Have you ever wondered how we can determine if two variables are related? The Spearman correlation coefficient provides an answer to this question. This statistical tool helps us understand the relationship between two things by identifying if they tend to move in the same direction, in opposite directions, or not at all. Let's take an example to make this clear. Consider the relationship between study time and test scores. The Spearman correlation coefficient can reveal whether students who study more generally score higher on tests, which is a positive correlation. Alternatively, it might show us that as study time increases, test scores decrease, known as a negative correlation. And in some instances, there might be no observable trend between study time and test scores, indicating a zero correlation. So Spearman correlation helps us figure out if two factors tend to move in the same direction, in opposite directions, or not at all. Now that we know what Spearman correlation is, let's delve into what kind of data it can be applied to. It's quite versatile, handling two main types of data with ease. First up, we have ordinal data. This is when we rank things in a certain order, such as survey responses categorized as poor, fair, good, and excellent. These categories are inherently ranked from 1 to 4 based on perceived quality. However, the exact intervals between these rankings are not quantifiable. The difference between poor and fair is not necessarily the same as between fair and good, because these differences aren't uniform or measurable. In a precise numerical way, we convert these ordinal categories into ranks. Spearman correlation is particularly useful here because it takes advantage of this ranking. By focusing on the order of ranks rather than specific distances between them, Spearman correlation allows us to analyze relationships within ordinal data effectively, even when the intervals between ranks are undefined. This makes it an ideal tool for interpreting the patterns and relationships in data, where traditional numeric intervals don't apply. Next, we have numerical data, also known as continuous data. Think of exam scores, which can range anywhere from 0 to 100. Just like ordinal data, we can rank these scores in ascending order. Spearman correlation then steps in to reveal if there is a relationship between variables like study habits and exam performance. Thus, whether it's ordinal or numerical data, Spearman correlation is all about the order of ranks, not the actual size of the numbers, like who comes first, second, third, and so on. By comparing these positions, we can figure out if two things are related without getting caught up in the exact scores or measurements. It simplifies things and still gives us the answers we need. Remember, you must convert your numeric or ordinal data into ranks if they are not already ranked. What makes Spearman correlation so practical and versatile? Well, one key feature is that it doesn't require data to follow a normal distribution. That's right. Even if your data doesn't resemble a typical bell-shaped curve, Spearman correlation can still come to your rescue. Again, this is because Spearman correlation is all about the ranks and not the actual values. When you assign ranks to a data set, each unique value gets a rank based on its position relative to the rest. This process transforms any data set into an evenly spaced sequence. So if you were to plot ranked data, each rank would appear exactly once, resulting in a flat, even line. This is distinctly different from a normal distribution, where data points tend to cluster around a central mean. So even if your data doesn't fit a normal distribution, you can still use Spearman correlation to understand the relationship between your variables. Let's talk about another key feature of the Spearman correlation. Now that we understand how Spearman correlation manages different data distributions, Let's see how it handles more complex scenarios where relationships between variables are not linear. Spearman correlation assesses the strength and direction of a relationship by using the ranks of the data points rather than their actual numerical values. This approach is key to its ability to handle nonlinear patterns. Look at these graphs: quadratic, cubic, exponential, and logarithmic. They show nonlinear relationships. The Spearman correlation is great when you suspect that your data follows patterns like these, where the relationship between variables increases or decreases consistently, but not necessarily proportionally or linearly. Another critical aspect where Spearman correlation proves incredibly useful is in its approach to outliers. Let's explore how this method manages these unusual data points. Outliers are the unusual values in your data that are much higher or lower than the rest. In typical analyses, a single outlier can have a big impact and can skew your results. But with Spearman correlation, we avoid this problem. How? By using ranks instead of the actual numbers. Take a look at this scatter plot. You can see a few points that are far away from the others. In a standard analysis, these points could dominate the result, but Spearman correlation gives these outliers a rank, just like every other point. This means that an extremely high score doesn't overpower the rest. It simply becomes the highest rank, and the same goes for extremely low values. This is how Spearman correlation keeps one or two unusual data points from misleading us about the true nature of the relationship we're investigating. Let's move to the practical side of things. How do we actually calculate the Spearman correlation coefficient? To explain the Spearman correlation coefficient formula, let's consider a simple example with 2 variables and 3 observations. Here's how we calculate the Spearman correlation step by step, along with a small table to illustrate. Suppose we have 2 variables, x and y, with 3 observations each. Step 1, rank the data first. We assign ranks to the observations in each variable. The highest value gets the highest rank. Step 2, we calculate the difference in ranks for each pair of observations. Step 3, apply the Spearman correlation formula. In the formula, D represents the difference in ranks between the 2 variables for each observation and represents the number of observations. After inserting the correct values, we calculated a Spearman correlation coefficient of 1. So, what does this value mean? Let's decode the values we might get from our Spearman correlation calculation and see what insights they can offer about our data. A coefficient of +1 shows a perfect positive monotonic relationship. As one variable increases, the other consistently increases. A coefficient of -1 shows a perfect negative monotonic relationship. As one variable increases, the other consistently decreases. A coefficient of 0 shows no relationship between the variables.